So hope everybody is safe in this pandemic, and today we'll solve some of the beam problems based on plastic analysis. Just a quick recap of the concept of formation of plastic hinge, and this time we'll try to explain the same by using the moment curvature relationship. So suppose we plot moment and curvature relationship of a specimen, and on the y-axis we have moment, and this my value corresponds to rotation that corresponds to the elastic limit. Beyond that will be the elastoplastic curve, and after this there will be a straight line. This corresponds to the plastic curvature or plastic portion. So what we see that after the plastic moment is reached, there will be increase in rotation without increase in the value of moment. So at this point what happens? Continuously deform as if it is having no moment of resistance, like a elastic hinge. So I will read it out. A state when moment is mp and the rotation of the specimen increases without increase in the moment, as if it has no moment of resistance, like an elastic hinge. So elastic hinge will not resist any moment, it will rotate. And formation of plastic hinge is a theoretical concept when the cross section, when the entire cross section is stretched to a value of Fy, because after Fy the stress is considered to be constant for a very high limit of strain. Now it will bring some clarity about the difference between plastic hinge and the elastic hinge, which we refer to as a real hinge also. A very simple example of it is the scissor. So this is the elastic hinge, and we know that elastic hinge is having no internal moment resisting capacity, resist any moment. It will simply allow the rotation about the hinge. So plastic hinge is rarely a true hinge, so it is a imaginary or a theoretical hinge having no capacity to resist moment. So once the plastic hinge is formed, it has no capacity to resist moment. For the plastic hinge, the internal moment resisting capacity of the section is mp. This is very important. For the formation of plastic hinge, this much moment equal to mp has already been resisted by the section. Then only it has become a plastic hinge. Now it is having no capacity to resist further moment. But for elastic hinge, the moment resisting capacity is 0. This is a very weird example, but it helps the students to visualize that all these are similar to fibers. When the entire cross section is yielded, that means stressed to Fy, internal moment capacity of such section will be 0, and it is free to rotate like a scissor or elastic hinge. Now the other common term is difference between structure and mechanism. Both structure and mechanism are combination of members, but in our civil engineering structures we don't like any relative motions. But whenever a load is applied on a mechanism, you will find that some part will move. Like in piston, it will move to and fro. This crank can rotate like this. So when a load is acted, civil engineers do not like that their structures move, whereas mechanical engineers design their mechanism that some movement is done. So in plastic analysis, what happens? At collapse, sufficient number of plastic hinges are formed which will convert the structure to a mechanism. Means there will be some motion between the members, and this is the state when the structure is assumed to break into links with large deformation. So when a structure is converted into mechanism, then we consider the structure to have collapsed. So mechanism is a situation when sufficient number of plastic hinges are formed in a structure so as to cause collapse without any further increase in the load. So we are not increasing the load, but still collapse will take place at this load. So this is the situation we define as mechanism. So mechanism actually results in instability of the structure, and it is manifested by the large deformation. So in a beam or a frame or a member, how we can say that deformation is large? we'll see by large rotation or deflection. Plastic collapse load. It is the load corresponding to collapse of a structure due to formation of plastic hinge transferring the structure to form mechanism. Means this is the ultimate load or limiting load at which plastic hinges will be formed and structure is converted into a mechanism. So the various types of mechanism are beam mechanism, panel or sway mechanism, it is seen in frame, gable roof like this, joint mechanism we can see in case of rigid frame. So this is a joint mechanism where joint is intact and it is rotated by some angle. So this joint is rotated like this. So this is joint mechanism, and the last one is combination, means combination of beam mechanism plus panel mechanism plus gable mechanism. So the sway mechanism and panel mechanism are same. Now we'll come to an important point, that is the theorem of the plastic collapse. We know that in plastic analysis, MP is the moment that corresponds to formation of plastic hinge, and once sufficient number of plastic hinge is formed, the structure will be converted into mechanism and the structure will eventually collapse. Corresponding to this value of MP, the load will refer to as the collapse load. Now suppose the load that is applied is less than the collapse load, so will refer to as the static or lower bound. Whenever the value is less than the collapse load, we'll consider the lower boundary or lower bound or static theorem. Whenever the load is greater than, whenever the applied load is greater than collapse load, it is called as the upper boundary or kinematic theorem. A unique case when load applied is such that it is neither upper bound nor a lower bound, it is satisfying both the theorems, that is it is equal to the collapse load. So we'll see then the theorem in plastic analysis. The first theorem is the static theorem or the lower bound theorem. This theorem states that when the load computed from any distribution of bending moment diagram in equilibrium with external load, means the structure is still under equilibrium, there is no motion with the external load, which is safe and statically admissible bending moment diagram, so that the maximum bending moment in any member shall not exceed the plastic moment. So the corresponding to the load, the moment that is generated is less than the value of plastic moment MP. So we can write M is less than or equal to the true collapse load. So this theorem leads to equilibrium of static method of plastic analysis. This method is also called as the safe theorem, satisfy equilibrium and plastic moment condition. So this is the diagram, and whenever the load applied is less than the collapse load such that moment developed is less than the MP, then we are referring to as static or lower bound theorem. Now the kinematic theorem means this theorem states that the load computed from any assumed kinematically admissible mechanism, that is, it is saying that kinematically admissible mechanism, that is, mechanism is already formed such that the load computed is greater than or equal to the true collapse load. So when mechanism is formed, it means that we are here, load applied is greater than collapse load. This theorem leads to kinematic or mechanism method of analysis. The theorem also called as unsafe. When for static and lower bound it was called as safe theorem, here it is called as unsafe theorem. A kinematically admissible is one in which deformation, that is slope, and the deflection under the load and support satisfy the principle of virtual work. Principle of virtual work says that internal work by the plastic moment at the plastic hinge is equal to the work done by the load on the structure. In case of kinematic theorem, we equate external work and internal work. So who is doing external work? So the load applied on the structure or a beam under consideration is the external work. How we get it? Load into displacement. And what is the internal work? So the section is trying to resist the deformation or the moment that is generated due to the applied load, and this internal work by the plastic moment at plastic hinges. So essentially we'll consider plastic hinge where the moment value is already equal to MP because mechanism is already created, value is MP and the corresponding rotation is theta. So internal work done will be MP into theta, moment into rotation. Now this is a unique theorem. Unique theorem is very simple. This theorem that if the load evaluated by static and kinematic theorem is same. So this is only possible when W is equal to true collapse load, WC. All the three conditions of the plastic analysis are satisfied. According to this theorem, there is only one unique solution for a given structure, while there are innumerable possible solutions with the other theorems. So at the case when W is equal to collapse or critical load, we'll get this line as the unique value for plastic analysis, that is W is equal to WC. Plastic collapse mechanism takes place in a beam. So first we take a cantilever beam. We know that mechanism of plastic hinge will be formed at the position where maximum bending moment is there. So for a cantilever, bending moment at free end is 0 and it is maximum at the fixed end. So this point where a circle is drawn, it is actually showing the position of a plastic hinge. So suppose it is a overhanging beam is there. So what will happen? Point load is here. So and moment will be there. So maximum moment is likely to be here. So this circle represents that it is a possible position of a plastic hinge. Similarly, if a cross section of a cantilever beam is changing, then also we will say that a possible position of formation of plastic hinge is 1 and the other one is this one. Now suppose we take a simply supported beam. So for a simply supported beam, bending moment is 0 at the support, it is maximum under the load. So it is showing that plastic hinge will be found under the load. So suppose this is a propped cantilever, so this fixed end is there. So here moment, negative moment will be there and here maximum positive moment will be there. So we'll try to explore both the position for the formation of plastic hinge and formation of mechanism. So this is a fixed beam. So these 2 points will have the negative maximum bending moment and under point load it will have the maximum positive bending moment. Suppose this is a simply supported beam with 2 point load. So maximum bending moment diagram will be like this. So maximum bending moment is here. So under both the loads we'll consider the possible location of plastic hinge and then we'll try to find the value. And here the cross section is changing. So whenever cross section is changing, we'll consider it to be position for a possible position of plastic hinge. So are formed at points where maximum bending moment is there at continuous supports. Like this is the continuous support. So then fixed ends, then these are the fixed ends. Then the rigid joints. So rigid joints are not in this figure and cross section changes like this. When the cross section is changing, that is the possible location of a plastic hinge. So number of mechanism, independent and combined mechanisms are to be determined, and independent mechanism will be mathematically equal to n minus Si. So n is the number of plastic hinges possible and Si is the degree of static indeterminacy. So how we identify a value of n? Simply draw the bending moment diagram, and wherever the maximum bending moment is there, the continuous support is there, fixed support is there, so there is change in cross section, we will assume it as possible plastic hinge location. So let us see the method of plastic analysis. The first method which we are going to see is the equilibrium or static method. It is based on the lower bound theorem, and the following steps we do. First thing, draw the free bending moment diagram, assuming that each span is simply supported, and then we will draw the redundant bending moment diagram. So based on the two bending moment diagram, we will try to identify the peak moment positions. So wherever the peak moment positions are there, and those points that are set to correspond to the plastic moment MP. Now the collapse load is determined by using equilibrium condition by equating the maximum simply supported bending moment to the plastic hinge at the corresponding point. So we'll take a look. So this is a case of simply supported beam, and here this is a simply supported beam subjected to a load W at the midspan, and this is the corresponding bending moment diagram. The central ordinate is the maximum, the value is WL by 4, and this is the deflected shape. So this place is having the maximum bending moment. As you know that in simply supported beam the support will have the zero bending moment. So these points will have zero bending moment, and because of any load the bending moment value will be 0 here. So this is the point where maximum bending moment is there, and because of the load this point will reach the value of MP, and this dot is representing the plastic hinge. So this will form a plastic hinge at the midspan or point where maximum deflection is there. And suppose in the case of a fixed beam, when the both the ends are fixed and it is subjected to a point load, then what we do, we'll draw the free bending moment diagram, assuming that this span is simply supported. So we draw the free bending moment diagram, and on that we overlap the end moments, fixed end moments at the two supports. Then we identify the peaks. So first peak is on the left support, other peak is at the right support, and the peak due to load is at the midspan. So there are three possible places where maximum bending moment is seen in the bending moment diagram, is the place for possible plastic hinges. So this is the first problem. This is from page 70, S.K. Duggar, our favorite textbook, and here we are considering the case of simply supported beam subjected to central point load. First thing what we have to do, we have to draw the bending moment diagram. So bending moment for a simply supported beam is a hut under the point load. So this diagram will get, so we have drawn it here. So central ordinate will be WUL by 4. The number of plastic hinges that will be formed. So this is a determinate structure, so redundancy is 0. So the value of R is 0, and number of plastic hinges formed is R plus 1, so it will be 1. So 1 plastic hinge is required for the collapse of this structure. So we'll write that maximum free bending moment is WUL by 4. Now simply we'll equate this value WL by 4 to MP, and we'll get the value of collapse load WU is equal to 4 MP by L. So this is a simple case. In this, what we have to do, we have to equate the free bending moment diagram with the value of plastic moment. So we'll get the collapse load. Then this is the second method. It is based on kinematic or mechanism method. It is based on upper bound theorem, in which what we do, we use principle of virtual work, in which we equate internal work done by the plastic moment with the external work done by the load. So it is basically a virtual method in which internal energy is equated by the external work done. External work done is by the load, and internal work done is by the plastic moment. So let's see how to solve the same problem. This is simply supported beam. So in this case, we'll draw the deflected shape. So deflected shape will be like this. Here deflection will be 0 because support is there, and here also deflection will be 0 as the support is there. So maximum deflection will be at the point under the load itself. So because of this WU, that is the collapse load, the deflected shape is going to be like this. It is not going to be curved, it is going to be deflected like this, and this will lead to the formation of a plastic hinge. Since it is a mechanism method or kinematic method, we consider that plastic hinge is already formed. So here the plastic hinge is formed, and we see that rotation at this end is suppose theta, and due to symmetry of the load, rotation at the other end will also be the same, that is both the ends will be theta and theta, and this angle will be sum of the interior opposite angle. So it will be theta plus theta 2 theta. and because of the load, the deflection under the load is delta. So we know that external work done is equal to load into displacement. So load into displacement, so we can write it as external work done is equal to W into delta, and internal work done by MP will be MP into 2 theta. So moment into rotation. So simply we'll equate this. So there are two unknowns, one is delta, another one is theta. So we'll use this triangle. So this length is delta, this is theta by 2. So we'll write tan theta is equal to delta by L by 2. So from this we'll put the value of delta as theta L by 2. When we solve, theta will cancel out and we will get W as 4 MP by L. MP value we can calculate by Fy into Zp. So now slightly change the question. Same simply supported beam we are considering, and again we will go back to our static or equilibrium method, in which we have to draw the bending moment diagram and simply equate the free bending moment diagram with free bending moment maximum value with the MP value. So this method is simple for standard cases where bending moment value is very obvious that this value will be there for the maximum bending moment. For complicated loading, the other method, that is the mechanism or kinematic method, is more suitable. So that method is more versatile than this. This is applicable for standard cases. So this is the bending moment diagram. We know that what will be the bending moment at this point under the load. It is W into A into L by L. So this value W AB by L we have to equate with MP. So when we cross multiply, we'll get collapse load WU or ultimate load WU is equal to MPL upon AB. So same question will solve with kinematic or mechanism method, in which we have to draw the deflected shape. So this is the deflected shape and this value is delta. Now the angles, because of unsymmetrical loading, the angles will be different. This is theta and suppose this is alpha. So the sum of interior opposite angle, this angle will be the sum of interior opposite angle, so it will be theta plus alpha. So we know that external work done is equal to WU into this delta, and how many plastic hinges are formed. Since here the bending moment is 0, so no way the plastic hinge will be formed in the case of simply supported at the supports. So only possible place is this point where maximum deflection is taking place and it is under the point load. So this has registered a moment equal to plastic moment MP, and in that the total angular displacement is theta plus alpha. So we can write internal work done will be MP into theta plus alpha. So from geometry what we can write is delta theta is equal to delta by A and alpha is equal to delta by B from this part. So we can write that, equate these two values. From both sides we will find the value of delta is equal to theta into A and alpha into B. Then we will simply equate this. So we will get alpha is equal to A by B into theta. So here in place of alpha we'll substitute this value and we'll get this. So ultimately we'll get the collapse load is equal to MPL upon AB, the same value we got from static method or equilibrium method. Instead of cantilever we have come to a propped cantilever. So this is an indeterminate structure and it is having point load. So how we draw bending moment diagram for an indeterminate structure? So it is drawn in two steps. First step is to draw free bending moment diagram. What is free bending moment diagram? Consider this span to be simply supported. So for a simply supported beam with a central point load, it will give a bending moment diagram as a triangle with the ordinate, central ordinate is equal to WL by 4. And then what we do will bending moment for the fixed end moment or the redundant moment we say. So it will be RB into L. There are two peaks. One peak is here and the other peak is here. Two possible mechanisms are there. First one is at the fixed end and the other one is at the point where maximum bending moment is there. So what we do, we have to now equate the maximum bending moment, free bending moment with the plastic moment. So free bending moment is WU L by 4. So WU into L by 4, and it is to be equated with the plastic moment at the section. So let us see what is the plastic moment at this section. See, this is the final bending moment diagram, and this value is MP. So for total length this value is MP, for half length this value will be MP by 2. So this outstanding portion, that is the net bending moment value, it should be equal to MP. So what is the total plastic moment at the section? It will be MP plus MP by 2. What is the bending moment at the section? It is WUL by 4. So simply we will equate the value. WUL by 4 is equal to MP plus MP by 2. So when we solve, we get 6 MP by L. Now same question we will solve using kinematic or mechanism method. So for this we will draw the deflected shape, and we know that there are two possibilities. First one is at the fixed hinge we will have a plastic hinge, and the other one is at this under the load. At these 2 points we got the maximum bending moment. These are the peak points for maximum bending moment, so we will consider plastic hinges to be formed at this section. So now what is the external work done? It will be due to this external load, it is WU, and what is the deflection? It is delta. So we'll write that external work done is equal to WU into delta. When the plastic hinge is formed, this will rotate by angle theta, and this is also has rotated by angle theta. So the exterior angle will be the sum of the interior opposite angle, that is theta plus theta, 2 theta. So we'll get MP into 2 theta. So here plastic hinge has, what is the value of moment? It is MP, and what is the rotation? It is 2 theta. And here the value of plastic moment is MP, and rotation is theta. So it will be MP plus theta and MP plus 2 theta. When we solve, equate, we will get this value. Now again come similar problem, cantilever with a concentrated load which is not placed at the midspan. So again what we have to do, we are using static or equilibrium method, in which what we do, we equate the free bending moment diagram and equate it with the plastic moment at the section. So it is quite simple. So what is the free bending moment diagram at this section? It is WU into AB by L. So W into A into B by L. And this portion should have moment equal to plastic moment MP, and for plastic hinge to form at this fixed end, it should have plastic moment equal to MP. So by similar triangle we can find this ordinate. So what will be the value? For a length of L, this height is MP. So MP by L into this length is B. So we will get this ordinate as MP by L into B. So what will be the total height of this plastic moment? It will be MP plus MP into B by L. So simply equate these two equations, and we will get MP into L plus B divided by AB. Same question will solve by using kinematic or mechanism method. So plastic hinge will not form at this simply support, it will be forming at fixed end. So here the plastic moment is MP, here again the plastic moment is MP. So how much rotation it resisted? It resisted theta. This angle is alpha, so this angle will be alpha plus theta. So what will be the internal work done? MP into theta plus alpha, and for this plastic hinge it will be MP into theta. So total internal work done is equal to MP into theta plus alpha, and this will be MP into theta. Similarly for external work done, it is load into displacement, so it will be WU into delta. Now from the geometry, we will use the geometry, and from this side we will calculate tan theta is equal to delta by A. Tan theta is equal to delta by A, so we will find that delta is equal to A into theta. And from the other side we will find that from this side we will find that delta is equal to alpha into B. So we will equate this, so we will get a relation between alpha and theta. So here in this equation, in place of alpha we will replace in terms of theta, and finally we will theta will get cancelled from the equation, and we'll get the value MP into L plus B divided by AB. So hope things are getting clear. Few more questions. This is a fixed beam, so this end is going to have maximum bending moment, this end is also going to have a maximum bending moment, and point load at the center. So three peaks we can see in the bending moment diagram. First one is the point under the load, and these are the two fixed end moments at the supports. So three hinges are formed. We'll check. If we consider the vertical forces only, we know that number of redundancy for this fixed beam will be 2, and R plus 1 will be, R plus 1 is equal to 3. So 3 plastic hinges are formed. So how we calculate it? Simply equate the free bending moment diagram with the moment at the center. So this is a straight line, this is a straight line, so this value is be MP and this value will be MP. So we'll get MP plus MP. When we solve, WU is equal to 8 MP by N. So same question using kinematic method. So we know that at collapse, internal work done should be equal to external work done. So this is the principle, virtual work principle, and work done by plastic hinge. So work done by plastic hinge is MP into theta, and work done by the load is equal to load into displacement. So how we calculate external work done? So it is WU into delta, and how many plastic hinges will be formed? One place is this one under the load, and the other two places are the fixed end, where we'll have fixed end moments. So these are the three places where plastic hinges will be formed. So now we'll calculate the internal work done. So moment into rotation, so MP into theta. For the first hinge it will be MP into theta. Again for this point it will be MP into this rotation theta, and this angle is 2 theta. Angle theta plus theta is equal to 2 theta. So this value will be MP into 2 theta. So when we equate this to value internal work done and external work done, we'll get WU is equal to 8 MP by L. This is a fixed beam subjected to a point load which is not at the center by the kinematic method. So we know that we have to equate the internal work done and external work done. So external work done is very simple. It will be equal to WU into delta. What about internal work done? It will be done by the plastic moment. So plastic moment will likely to form at fixed end under the point load and this fixed end. So what moment, what angular displacement is there? It is plastic moment is equal to MP. So for this portion it is MP into theta. For this portion it is MP into theta. For this portion where the angular rotation is alpha and plastic moment value is MP, for this portion it will be MP into alpha. So MP into alpha. So under the load the rotation is equal to theta plus alpha, and the plastic moment value is MP. So we'll get the value as MP into theta plus alpha. So when we equate this, we'll have two unknowns, alpha and theta and delta. So what we should do, we should convert everything in the form of theta only. So we can write from the left hand side, we can write tan theta is equal to delta by A. So delta will be equal to A into theta, and from right hand side delta will be equal to alpha into B. So equate these two values, so we'll get a relation between alpha and theta, and in place of WU into delta we will write, in place of delta we will write A into theta. So from the entire equation we can cancel the value of theta, and in place of alpha we should write theta. So finally we'll get this value. So this is a slightly different question. It is a cantilever beam. The redundancy is 0 because it is a determinate structure. So number of plastic hinge formed is 1. So since the beam is having non-uniform cross section, there are two possibilities of plastic hinges. One will be at this point where the section changes. So plastic hinge will be formed at this section at the weaker part, and other point where plastic hinge could be formed is at the fixed end. First we will consider this one. Suppose the plastic hinge is formed at the point where cross section changes. So what we do, we will calculate the value of internal work done. So only one plastic hinge is formed. So what is the value of plastic moment? It is mp, and suppose rotation is theta, so it will be mp into theta, and load acting is 2w, and what is the displacement? Suppose it is delta. So we can write external work done is equal to 2w into delta. Now in place of delta from this triangle, we can write tan theta is equal to delta upon L by 2. So since value of theta is so small, we can write tan theta is equal to theta. So cross multiplying it, we will get the value delta is equal to theta L by 2. So here in place of delta we will put this value, and eventually we get mp into theta is equal to this value. When we solve this, we get collapse load is equal to mp by L. So 2 will cancel out and we will get mp by L. So now second case will be the plastic hinge can form at the fixed end where maximum bending moment is there. So value of plastic moment is equal to mp, and the value of theta is suppose theta only. So from here we can write tan theta is equal to delta by L. So delta is equal to theta L. So what will be the external work done? It will be 2w into delta. So we'll write external work done is equal to 2w into delta. So in this case the value of mp was mp only, because the plastic hinge was formed at the weaker section, and here the plastic hinge is formed at the section which is having the mp value is equal to 1.5 mp. So we will write the internal work done is equal to 1.5 mp of theta. So how we change the value mp? So it is based on zp value. So here we are putting a heavier section, and here we are putting a lighter section. Thus we can adjust the value of mp. So wc is equal to 3 by 4 mp by L, or 0.75 mp by L. We should compare these two values. From case 1 we got value as mp by L, and from case 2 we found that value is collapse load is 0.75 mp by L. So the lesser of the two values will be our collapse load. So now this is another problem from SK Dupil. It is question 2.4. So this is a fixed beam, and first thing what we should know is how many plastic hinges will be formed. So its value is r plus 1. So what is r? Since this is a fixed beam, the degree of indeterminacy is 2 when we are considering vertical load only. So r plus 1 is going to be 3. So first position is fixed. This end will have a plastic hinge. Similarly, this end will have a plastic hinge, and at this point also there is possibility that plastic hinge will be formed because there is change in the cross section. So where should the plastic hinge should form? At stronger or weaker? So it will be formed at the weaker section. And the last option is plastic hinge can be formed under the point load where mp value is twice of that of the right side portion. So let us solve this. So the given section is non-uniform, and there are possibilities that at the point where section changes in the weaker portion there will be formation of plastic hinge, and other is at the point of application of load, under the load there is possibility of plastic hinge, and at the fixed ends where maximum bending moment, negative bending moment is there. So let's solve it. So case 1 is 2 plastic hinges are formed at ends and one at the place where, so these 3 points we are considering. So for that, so these 3 points we are considering. So suppose the load is W, so external work done is equal to W into delta. So no issues with that. Now this is the plastic hinge, there is plastic hinge here and there is a plastic hinge here. The value of plastic moment is MP here, On the left hand side it is twice MP, on the right hand side it is MP. So it will be formed in the weaker section. So the plastic moment is at weaker section is MP only. On this side it will be twice of MP. So now let's multiply the value with angular rotation. This angle is theta and this angle is also theta, and this value we have taken as delta. And suppose this is the central displacement. For this point we will get twice MP into theta. For this point value will be MP into theta. Here the angle is 2 theta, so for this point we will get MP into theta, 2 theta. So this is the equation. Simply we have to equate it. From the geometry we can find that this theta and delta, relation between this theta and delta, and we'll substitute this theta here and we'll get collapse load as 15 by L into MP. Second case will be when plastic hinge is formed at fixed ends plus under the point load. So at these two places value of plastic moment is twice MP. Here also the value is twice MP, but here the value is MP. So external work done is equal to W into delta. Suppose it is theta and on this side it is alpha. Here the angle will be theta plus alpha. So what we can write for this point, it is 2MP into theta. For this side it will be MP into alpha. Here the angle is alpha plus theta, so the value will be twice MP into theta plus alpha, and external work done will be W into delta. So these two equations we have got. Now we have to find the relation between theta and delta. So by geometry we will find that theta, delta and alpha also. So three values we have to put and equate the value of delta to the both side, and we'll get relation between theta and alpha. So eventually we'll get the collapse load as 16.5 MP by L. So we considered two cases for this question. Now the first one yielded us the value of 15 MP by L, and the second case yielded the value as collapse load at 16.5 MP by L. So we will find that the minimum of the two values, that is two plastic hinge at the end and at the point where cross section of the beam changed, that position will take as location for plastic hinge. So I think that is all from my side.